Hey guys, today we'll be learning Softmax. So in Softmax, what we do is we change a set of an array of values, numerical values, into a probability distribution. So our exposition today will be understanding how Softmax works, how Softmax is computed, and both the aspects are important because we usually study them in a disjoint manner, but we'll study today in a combined manner, and that is very important for your understanding, for creating that connections in your brain. So let's get started. So what is Softmax? Softmax starts with an array of values, numerical values, and it changes into a probability distribution, a probability mass function. For example, here it will be 0.09, 0.25, and 0.66. So these numbers are changed into a probability mass function, a probability distribution. So how to write it mathematically? First, you have this x1. So if you want to generalize it, you want to write it as x1, x2, xn as a list of numbers, as an array of numbers, and you want to change it into probability p1, p2, pn. Right? So you want to change x1 dot x2 dot xn to p1 p2 dot pn. So there are many ways to do it, but Softmax uses a very specific exponential manner. So what they do is the following. So they first change each of them into exponential powers of each. So I think I need to make it a bit larger. E to the power x1, e to the power x2 dot e to the power xn. First it changes into that, and then it sums all of them up to create a summation. S is equal to summation of I from 1 to n numbers, each one of them. Okay? And then it does the following. It combines them to create, so how to change this? Now you divide each of the numbers by this sum, so the sum of all these numbers will become 1. So you make it e to the power x1 divided by this s dot e to the power x2 divided by s e to the power xn divided by s. Okay? So now you can observe that if you sum all of this up, you get s in the numerator and s in the denominator. That cancels out to give you the probability distribution, because the summation of pi should be 1 and greater than or equal to 0. And each pi should be greater than or equal to 0. So you can say that exponential, make sure it's greater than or equal to 0. It's 0 only happens if it's it's negative infinity, to be honest, but practically speaking 0 happens when the number is very negative. So this is the basic mathematics of Softmax, okay? But there is a catch, which is from a computational point of view. The catch is, what if the number becomes very large? Okay? What if the number becomes very, very large? Let's say 1000. Then the floating point operation e to the power, in fact, e to the power 100 is around 2.7 into 10 to the power 43, if I'm not wrong. That's a lot for the computer to store, even for that. Imagine 10 to the power 10, that will be more. So the basic idea is the following, that we want to make sure that the computer doesn't go into this huge number, how does it go into this huge number aspect, okay? So we have to make sure computationally, numerical manner, we settle this issue. So what do? So we do the following. Before doing this, we will follow the exact same steps, but we will subtract. First we will calculate the maximum. M is maximum over all these xi's. Okay? And then we will subtract it. That we will calculate x1 minus m, x2 minus m, dot xn minus m. it's requested that you should take down notes because it helps you keep the context in your mind. Okay. And now we do the exponentiation. So we do calculate e to the power x1 minus m, e to the power x2 minus m, or not e to the power xn minus m. Now why do we do this m subtraction? Just to make sure that the maximum is subtracted. So if the maximum is very large, okay, if the maximum is very, very large, it will make sure that the maximum is now less. Its maximum is actually less than equal to this. All of them becomes less than equal to 0. Okay, so this is now well maintained in its own computational paradigm. But since this is normalized by the summation, that e to the power minus m that you multiply with each here will get cancelled. That's maybe a small exercise for you. So what do we do now? We take the summation of it. S is equal to summation of e to the power xi minus m for all I from 1 to n. And then we combine these two to calculate the following. E to the power xi minus m divided by s, e to the power x1 minus m, x2 minus m by s, the power x2 minus m divided by s, dot dot dot, e to the power xn minus m by s. Okay, we do the steps and then we get this turns out to be probability, and we also settle down the computational aspect. What's next? So this is the basic mathematics. But we will not stop here, as I said. We will also focus on the computational aspect. So we will understand how to also do this in a framework like Torch or NumPy. Okay? And there are two sub aspects of it, and we will come to that each one of them. So stay tuned. So remember this. So now we will write this in a vectorized form. I have small space over here because otherwise you will not be able to, if I move it to a larger board aspect ratio, then you will not be able to see the math equations. So we have to make sure we cover only one aspect of the board, one part of the board. So to understand what I'm saying, you have to take down notes. It's very important. So observe this now, that how do we now do it in a vectorized format? Now you see we are doing this exponential operation over and over again, so we don't want to repeat it. And PyTorch or NumPy or JAX, all this framework gives you the vectorized operation. Okay, and we will explore that too. So usually you think that I'm going to code. No, I will not code. So I'm trying to help you understand an alternate language system which is similar to the mathematics, to the coding that you will do. Okay, I will not use the exact np.sum, I will use sum. I will not use np.exp, I will use exp, exponential. Okay, and I will use a similar notation so that you can connect it to the code, and this is very important. And I believe this needs to be done in mathematics while you're discussing machine learning, because this is what helps you connect both the aspects and not learn it individually and in a disjoint fashion. And this is very important, guys, I'm telling you. Because most of the errors when you use GPT to code happens because of this linear algebra mismatch, this dimension mismatch, okay? And you will see how important it is to track each of the dimensions individually. So what we will do is that, to make sure, to just make you understand that a variable x, a single number, is different from a tensor, a multidimensional x, we'll just put this vector kind of notation, which we used in physics classes, but we will use it for brevity here. So what we'll do is that we will write it as x tensor, but the tensor dimension is n. So this is very different from this. So that's why we need to introduce that notation. Okay, the vector notation here. I forgot what it's called. So we introduce this. So this is a vector which is of dimension n. This is of dimension n, and it is a vector. Okay. So first this is of dimension n, and then we calculate the sum of it. So we calculate the sum. We calculate the maximum. So we calculate the maximum m, which is max of it's a function, max of this n dimensional vector, and this turns out to be of dimension 1. Because all the n numbers, we have only one dimensional max. So what we do is here, we now do we now subtract xn this with m. So we use this 2 to get. Now this should be, if you remember, each of the elements should be subtracted by m. So this gives you n. So you can see, how can you subtract a n-dimensional vector from a one-dimensional scalar? You cannot. So this is what internally PyTorch and NumPy uses. It's called broadcasting. This is where broadcasting is used, where this is expanded into at the n-dimensional and then subtracted. Now it doesn't expand it in a memory, so there is a memory constant out there. Let's not go into too much details, but mathematically it expands it into all the n dimensions and then subtracts it to get this, exactly what we're doing mathematically. But it's important to connect to the computational aspect. So we get, rewrite it, we get xn vector from their m, which is one dimensional, the max, and then we subtract it xn minus m to get another n-dimensional vector, and so you can rub it off if you want, but they are the same. And now we will do exponential of it. We will do exponential of each one of them. So we'll do exponential. So when you call a function like this, it does it element wise. So if you remember, each of them was e to the power xi minus m. Each one of them happened x1 minus m, x2 minus m. So it is actually essentially doing this. Exponentiation. So for brevity, what we usually do is we give it a name. Let's call it normalized. So capital N of n is equal to this. So that, and here we do this normalized. We are normalizing by the max, the exponential of that. Okay? And then, so again for brevity purpose, it's an n-dimensional array. Let's give it a variable name. So this n, so give it a name, a vector notation. So it's a vector. It's exponential of, see, I'm building a mathematical notation for this so that you don't have to always sit in front of the code computer to do this. You can think it in your brain and then let it code it. It's like a pseudocode version. Exponential of this normalized version. Okay? And then also we need to do the summation here. So S, which is a single number, so it's 1, is sum of, I'm not using the summation notation here because I'm doing it in the coding manner. This n of n, the normalized one, yeah, so you sum it all up, n of n. You sum it all up along this. And then here you get the final p bar dimension n, this one. So let's call it p bar dimension n as en bar by s1. So again there is a broadcasting here because it's of n dimension, this is of one dimension. So it's applying on each element wise, okay, to get the final probability. So this is the final result. Very good. So this tells you the entire structure of how the NumPy codes. But in deep learning, it happens in batches. So you will not get just a vector, but a batch of vectors. Okay, and then you have to transform it in all the batches in a parallel fashion, right away. So we will now do that. That is very important. Okay, that is usually not taught and discussed like this, but it's very important for you to have it. If you do it for a few examples and you get a grasp of it, It's very important for you because then you can extend it, generalize it to other cases, and it will build it into your veins, in your nerves forever. This type of language, okay, this mathematical pseudocode, it's very important, guys. So now we will do it for batches, okay. If this is too much for you, I would suggest you to like read this, take a break, and come back again tomorrow or day after tomorrow to again attend to this. But completing this entire lecture is very important for understanding Softmax, how it happens in B batches. So now we will do it in B batches. Good. Again, I'm rubbing it off. Some new aspects is coming, and it's going to be very much fun. Okay. So now, instead of this framework, you have I'm not writing it, but you have, imagine it now, these vectors of all those numbers. Okay? Is a vector. It's like a matrix. So you have B, N. So N dimensions here, and B of them here. So this is axis 0, and this is axis 1. N dimensions and B dimensions here. So we call it Bn. So let's give it a name. So let's call this capital X Bn and give it a vector. To note it, it's a tensor. Now we will, what we want a similar P. So we want a P tensor, but again same dimensions. We want to change each. Now understand, each one of them is actually moving it here. So that's the trick. How to do that? Okay, each one of them is moving along the axis 1, but not along the axis 0. And this is where the fun happens. Okay, this is where the mathematics makes the computing in PyTorch and deep learning, PyTorch and NumPy, and this vectorized operation. So with this probability is PBN, P again of Bn, same dimensions. How do we do this? Very simple. We will follow the exact same steps. So let me repeat. We have an X, remember. Then we calculate the maximum, okay, M. And then we calculate the X minus M in some sense. And then X minus M not in some sense. Then we did the exponential. And then we did the exponential divided by the summation. Oh, I forgot the summation. So here we did the summation. Sorry, we did the exponential, we did the summation here, S. Okay, and then we got both of this to get the final probabilities. So this was the framework, right? But here we have to make sure the dimensions are all right, are aligned. So what we will do here is, we have this X tensor Bn. Okay, we have this X tensor Bn. And what we want? First is we going to have the maximum. So we calculate M again, but what we want a maximum of what? We want the maximum along each of the rows. So M will be of B dimension, but also have one column. So B1. And this will be the maximum of naturally this entire XBN, but there is a catch. It's when you're not doing the maximum over all the entire matrix, you're doing along each row. So there should be a variable for that. There should be a language for that. So there is axis. So we are doing axis what? Along which axis we are doing? We are doing along axis 1. So here is another aspect. It's very easy to understand what is axis 1, what is axis 0 here. So you also have to think in, let's say there are 5 dimensions. Then you have to also think about along which axis it's happening. Okay. So an interesting way to think also is which axis is getting compressed. So you can see that this axis is getting compressed. The axis 1 is getting compressed, reduced. So you can see axis N, the second axis, the first axis, this is axis 0, this is axis 1. So this is getting compressed to, the N is getting compressed to 1. So hence its axis. So you can first write the algebra and then figure out the axis if it's an issue for you, okay? So in tensor mathematics, this has been used in physics a lot. So this is called this way of writing is very equivalent to Einstein notation. Okay, not this exact thing. Einstein notation is about contraction and other stuff. But this approach, this habit will help you work with vectors and tensors in a very useful manner. Not only it will help you write the math, but also it will help you write the code. That's the beautiful part. So it connects both. Okay, that's the most beautiful part, guys. So remember this Einstein notation if you are interested to study it a bit farther. So we have Bn, which goes to B1, and so we are reducing the axis 1. Okay, we are reducing the axis 1. So we have this max. Again, it's the same thing. They will be broadcasting along the axis 1. Each of the ends, each of them will be subtracted by the m, the maximum. Okay, because it's at the same maximum. So we get the max normalized, which is also of Bn, which is nothing but x of Bn minus m of, I hope it is visible from here, m of B1. So along the axis 1, it is getting replaced. Now we have the max, this normalized, we will have the exponential. So let's write the exponential, E. Again, exponential is happening across each of the rows. Sorry, I'm wrong. Exponential is happening across the entire matrix. Everywhere it's exponential. So there is an axis concept here. So E, again tensor, NB is equal to exponentiation of the entire NBN tensor. Okay? And then we are doing summation. Again, the summation is along each of the rows. Okay? Each of the rows. Along the axis 1. So axis 1 is getting reduced. So S. Now the summation will be again of dimension B1 is sum of NB. Axis is equal to 1. Okay? And then we combine these two to get the final P tensor NB in dimension is nothing but. Now again, broadcasting is happening here. It's a, sorry, what I'm doing. It will be Bn. Did I rewrite? Yeah, Bn, sorry. I hope I didn't write NB somewhere. I don't think so. So now you can see here I have written NB, so it will be Bn. So it will be E Bn by S vector B1. And you can see again n and 1 are essentially broadcasting. When does broadcasting happen? When wherever there is a mismatch, at least in one of them there is 1. Okay? In wherever there is an axis mismatch, the dimension of the axis mismatch, wherever there is a mismatch, one of them should be 1. Then it will be broadcasted. Okay? And this will give you the final probability. I know this has been a bit different, a bit hectic probably, a bit convoluted if it's for you. It's because you're connecting both the dimensions of mathematics and computing. And this approach has helped me to understand it very well. I'm now teaching it to you for the very first time so that you can combine this mathematics and computational aspect in the same format so that you don't have to think twice before coding. So this format will really help you if you learn to write in mathematics, and people have been using this format in physics for a long time. Okay, the physicists have been doing this for a long time. This notational format for tensor calculations. Visit Einstein summation to understand how deep it is. I will see you in the next video. I hope you enjoyed it. Bye bye.